Good morning, everybody.
Good morning, Bob.
Wow, what an enthusiastic bunch. Not a very big bunch, but an enthusiastic bunch nonetheless. Welcome to our 2018 dress rehearsal for National Chemistry Week. Very interesting program this year. But before we get there, let me just give some kudos out. Thanks to John Carroll University, as always, for allowing us to use their facilities on 2 different occasions. Thanks to all of you for coming. I think everybody that's here helped at GAC Day, so we appreciate that. And I want to acknowledge members of our planning committee. I see Marcia Shealy over here. Sharilla Singham is behind the camera. Sharilla, you going to come out sometime and say hello? No? Okay, she's quiet back there. Bob Williams is here, and Lois Kuhns is over fixing up some last-minute issues with the kids. I'm Bob Fowler. I'm sort of the cook and bottle washer, chief cook and bottle washer for the whole thing, and we do have fun. Right, Robert? Mm-hmm. We have a lot of fun on our planning committee. If anybody wants to join our planning committee, by the way, you're more than welcome. We meet like twice a month from April to September. Okay, as far as this year's program is concerned, the national theme from National ACS was chemistry is out of this world. So at our first planning committee meeting, we thought about what we ought to be doing, and we said, well, we've got a NASA research center over next to the airport. Some people know about that, and some people have been associated with it in the past. So what is going on at NASA? Well, it turns out a mission to Mars is potentially, at least, in the offing. There's some work being done on that right now, all right? A little bit is happening. So we said, since we have our very own NASA research center here, and since a mission to Mars might be in the offing, we thought that a good expression of the national theme might be a mission to Mars. Now, how do we effect a mission to Mars here in our laboratory setting? Well, we thought the best way to do that would be to give the students some idea of what it would be like to live on Mars. Maybe a little bit of a sense as to how to get there. We have something up our sleeve for that. But the rest of the program is really about what it's like to be and live on Mars. And is the Mars environment different from the Earth environment? You betcha. Everybody knows what Earth is like. I went out and cut the grass yesterday, thought nothing about it, walked right outside, turned the lawnmower on, started cutting the grass, and did my thing for a couple of hours and didn't think a thing about it. If you did that on Mars, you'd be dead. The average temperature on Mars is minus 80 Fahrenheit, average temperature. It swings quite a bit. The atmosphere is 96% CO2. The gravity is about 1/3 of that on Earth. And what you see on Mars, if you look around, is red dunes and plains. And the Martian environment is subject to dust storms. I understand from looking on the NASA websites that there are dust storms that well up and can last for months, right, Carol? I mean, it's unbelievable, and it's full, the storms are pretty severe, and they're full of abrasive dust. So we're going to be looking at a lot of things today. We're going to be looking at how do you get power on Mars? Unless you have a real long extension cord from Earth, you've got problems. There aren't any generating plants there yet, as far as we know. How do you go outside and cut the grass? Is there grass on Mars? Well, of course not. There's no grass on Mars. But how do you go outside? Well, you have to have some kind of a spacesuit on, okay? And we're going to go through a lot of experiments like that, but we're going to start with why is Mars red? And even before I do that, let me call your attention to a couple of things. Up here, Sherman, if you could zoom in on this right here. This is the local section website that has all of our NCW information on it. It has copies of this script in living color. You might want to think about going out and printing your own copy. There's an errata sheet out there as well, and it turns out there's several little minor errors that can become major errors if you don't use the errata sheet. So my recommendation is to go out to the website right up here and print yourself a copy of the script, even though there are black and white copies like this one in each of the kits. There are inaccuracies in there, so I suggest you go to the website and print a new one, or at the very least, get a copy of the errata sheet and apply it to the hard copies, which is what this is supposed to go with. Okay, so let's go to the very, very first experiment, and that is, why is Mars red? Well, it turns out that if you look with your naked eye up in the sky, I think it's, you can see Mars, and you can see that it's twinkling red. It turns out that on, I think, October the 17th this year, is that a Saturday? Whatever, October 17th, if you look up in the evening sky and look at the moon's going to be like a quarter of a moon, and 6 degrees to the left and above the moon is where you'll see Mars on October the 17th. It'll be very, very apparent. And it's obviously red. Well, why is Mars red? Why are some of the features on this planet red? My family and I took a trip out west a couple of years ago. We went to Bryce Canyon National Park. As you drive in Bryce Canyon, you drive through walls of red cliffs. Why are they red? Well, let's try to answer that with experiment number 1. At the center of each table, there is a white sheet of paper with 4 cups on it. That's going to be our experiment number 1. And what I'd like all of you demonstrators to do, even at this point, I guess, is to give the students at each table a number. Hopefully you're going to have 5 students at each table, and let's give the students numbers. Let's go like 1, 2, 3, 4, 5, 1, 2, 3, 4, and since we're going to need a 5, Bob, you're going to serve as number 1 and number 5, okay?
Nice good personality.
Well, whatever. I mean, whatever works, Bob, under the circumstances, I guess. Okay, so student number 1, if you would take the cup marked F1 and make sure it's in the center. No, actually, let's put it back. Let's move these cups out of the way. And let's put that in the center. What we're going to do next is student number, I beg your pardon, number 1 was supposed to put the white paper in the middle, it's already there. Number 2 puts the cup in the center, it's already there. Student number 3, if you pour the vinegar from cup B1, Victor 1, onto the iron filings that are in cup number 1, and kind of just pour it all in, right on top of the iron filings, and swish it around a bit. Student number 4, if you would take the cup marked S1, Sam 1, and sprinkle the salt on top of the iron filings in cup F1, and sprinkle the salt in there and swish it around. And student number 5, if you would take the cup marked P1, Peter 1, and pour it on top of the iron filings and swish it around. Let's wait for a second and see what happens.
Water?
Pardon me?
P1.
That was peroxide. First we put vinegar in the solution. This is thanks to Dr. Singo. She came up with this one. First we put vinegar on the iron filings. Then we put salt as, I guess it's a bit of a catalyst, right? And on top of that came the peroxide, the strong oxidizing agent. And what you're seeing in front of you is the iron filings, which of course started out being black, being oxidized to iron oxide, which is red.
Yes.
So at some point,
Bob, I'm giving that a wow factor of 7. Yes.
you give it a wow factor. So one of the things we always do, all you demonstrators out there, is we have Well, we have a student member of our planning committee. She happens to be a sophomore in high school. She's the daughter of one of our members. Well, they're both members at this point. But we always ask her, whenever we come up with an idea for an experiment, what's the wow factor? Because you remember, we're dealing with kids here in grades 2 to 6. And 2 to 6-year-old kids, what we're trying to do is interest them in science and in chemistry. And if they see a bunch of dud experiments, they're not going to be too awfully interested. I always, when I make the presentation, I always keep stressing the fact to the kids, chemistry is boring, right? Chemistry is science. Nobody likes science. But it turns out that what they're doing can be a lot of fun. So this is one of the things that our student member came up with that, in fact, her name is Katie. Thank you, Katie, for all the work that you did with us. She came up with a high wow factor. I don't know if she gave it a 7 or not, Vince. But anyway, Vince now gives it a wow factor of a 7. And hopefully the kids will like some of these things.
I would point it out too, if you feel it, you can feel an extra.
Really? It's getting warm too, okay. Exothermic reaction. Okay, next thing we're going to do is we're going to jump experiments. We're going to jump to experiment number 5 because Vince Opaskar, who is a member of our planning committee, did I point you out at the beginning, Vince?
No.
If not?
I was absent.
Okay, well, you're present now. Vince is going to show us how to perform experiment number 5. We've done this quite a bit in the past. It turns out that you're going to need propulsion to get to Mars. It could be argued that in the order of our experiments, perhaps the propulsion experiment should be the first thing we do. You know, obviously that's the first thing you do in a mission to Mars. You've got to get off of this planet. But, as you'll see in a second, the propulsion experiment number 5, requires all the students to get up and come over to a launching pad, which, Shamil, I don't know if you can see that or not, but there's a blue tray down on the floor here. It requires the students to get up and come over to the launching pad, and that's going to cause a little bit of disruption in the room. So we thought we'd keep those kinds of disruptive experiments to the end, okay? So hence, our rocket experiment is number 5, and it's toward the end. And there's just one after that. There's 6 experiments this year.
And Vince was heading out of order due to a scheduling issue.
Yes, Vince has to depart shortly.
It's not the scheduling issue as such, but it has to do with the sequence of the different demos. We have to use a little more time at another location, another demo. I forget which one it is at the moment, but one that takes up a lot of time.
Oh, yeah, number 3 takes a lot of time, turns out.
Yeah, we have to come back to it.
Okay, yes, that's true. But Vince has to get going. You got a daughter getting married in Montana.
No, they're all married.
So Vince, take over number 5, if you would, please.
All right, where's that book? The catalog. Got the numbers. Now, I'll give my son a plug. He's a graphic arts designer. He's 40 years old. He hasn't had a steady job in his whole life. And he came up with an invention called Snap Pets. And a single piece of cardboard, if you fold it, and tape it, and assemble it properly, it comes out so that the mouth of the originator is intended to be a dinosaur, which it is. And it's just a head and a structure, and it goes snap, 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 snap. Well, the hockey team here in Cleveland picked up on it, and this is a worldwide debut. At the 1 o'clock.
The debut at 1 o'clock today. Okay, Vince. So much for the commercial.
Okay, so much for. Thank you.
Go for it.
I want to get the proper numbers corresponding to what's already on the table.
Well, there isn't too much. There's just a paper towel with a canister on it. Everybody has one.
All right, we'll take the.
And a cup in the middle with A5 on it.
We're going to take the canister, open it up.
Actually, Vince, there's one here on the demonstrator's table for you to use to demonstrate.
Top. Oh, make sure you wear your goggles.
Oh, yeah. they're not wearing goggles, they can't play the game.
And, okay, we're good. We're going to pour half of this canister full of water. So we're going to use the W.
It's already half full.
Got water in there.
Mine doesn't have it.
Right.
Oh, yours doesn't because it's a demo cup.
Okay, and at this point, you want to stop and really put the word out to all the kids that you could get hurt if you don't pay attention to what's going on. Step by step, we're going to do a dry run, and then we're going to add our ammunition, which is the A5. It's a chip of Alka-Seltzer. And as I said, we're going to do a dry run so that everybody's up to speed. So if you want to grab your canisters, we're going to stand around on the
Table by table.
table.
Table over here first, please.
We'll do this table first.
And have the students gather around the tray on the floor, which you, Ms. Demonstrator, will have put in a spot where you can't do much harm if it hits something up above, like lights or something.
But not around, actually some distance behind.
Yeah.
Coming forward.
Yes, around and away from the tray.
Did we have the car?
We have extra paper towels.
There are big towels on the,
Okay.
you don't have one, but they do.
All right, we're going to put this in just to soak up the spillage that's going to happen on eruption day. All right. Okay, so now we've got, everybody got their goggles on and everybody's got their water in the canister. What we're going to do when we get going on this thing, the first step is to practice putting the top on. So try that.
Believe it or not, you do need to practice that, because once the action starts, when you put the Alka-Seltzer into the canister, the kids immediately start fumbling around like, oh, the world's coming to an end. So have them practice putting the cap on and off a couple of times before they put the Alka-Seltzer in the water.
Okay. So you know you're guaranteed a snug fit when you hear that little click sound. Okay. Now, what you're going to do once we put the Alka-Seltzer fill in, we're going to put that cap on, and we're going to bend over quickly and take 2 steps back, get at least 5 feet away from the launching pad, and wait 15 to 30 seconds for this thing to rumble and pop.
Vince, you gonna turn it upside down?
Yes.
Yeah.
He has it upside down.
Do you have it upside down?
Yes.
Yeah. So,
Okay.
let's practice that. Putting it on, putting it off.
This would close the whole
Put it
body.
on, and march up to the tray, touchdown. All right.
And stand back and don't come anywhere near it until the things pop.
Okay, now let's go back and pick up our Alka-Seltzer. Take one. Take one. I'm not giving you music. One. 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 Okay, so if we all do this in succession and they all happen at the same time, we'll put 5 of them up in the ceiling. So here we go. Any questions? Okay, let's put the Alka-Seltzer into the water. Put the lid on. Snap it. Upside down.
And stand back. And everybody's got their goggles on at this point, right?
Yeah. There's one. Wow. 2. 3.
Wow!
There's one more, there's one more.
Wow,
There's
wait a
one more.
minute. Now, this may happen. If there's one that doesn't want to pop, keep the kids away from it, please. There we go.
There it goes.
It will eventually pop. If it doesn't eventually pop, you, the demonstrator, should go and pick it up, not one of the kids.
Okay.
Because it could, theoretically, I guess, take an eye out.
Yeah.
So be very, very careful, even with goggles. Do not let the kids approach them until they blow up. Now, at this point, the fun starts, because now the kids have to retrieve the body and the top of each one of their canisters.
All right, so let's go on a hunt and find this.
Yeah, you might want to tell them to kind of watch where everything goes once they pop, because they get to go and retrieve everything. And they can take these canisters home with them.
Alka-Seltzer, not supply.
I wish they wouldn't.
We can get, we did.
There's one more missing.
Yeah,
We
Greg had
had
enough trouble with them
elevations
together.
just on the
Oh.
30-foot area. This is what, probably a 15-foot ceiling,
Yeah.
so double that, and we can pop it. Secret, if you want, use a little more Alka-Seltzer.
Are you kidding? You blow the roof off the place. Okay, table number 2. Okay, students, please have a seat. Table number 1, table number 2. Come on down. Now you've heard the routine. Actually, Vince, I don't know if that paper towel is helping any. I don't know. But it just gets soaked just immediately. Yeah.
Yeah, get rid of it somehow, so this is as good as that.
Yeah, just.
Okay,
Are you ready?
we have 4.
Who's got the Alka-Seltzer cup?
Get the Alka-Seltzer.
Oh, everybody got it? You guys are ahead of the game. Everybody's got a piece of Alka-Seltzer? Have you practiced putting the top on and all?
Yeah.
Yes. You guys are good. You 6th graders are good.
All right, goggles, material, Alka-Seltzer. All right, we can, ready, set, go. Drop them in, cap them up. Check your goggles. Step back.
Oh, there's a dud. There's a dud.
Mars popped already.
At least I'm gonna go far.
And when you're putting it down, avoid putting your face directly over the launch pad, so that if one does go off prematurely, it doesn't catch you.
So we had 2 duds or 1 dud?
One dud. One
That
dud.
means the cap wasn't on tight.
One was aborted,
Probably,
and one's a dud.
yeah.
It's
Wait,
leaking.
wait. Oh,
It did
oh.
get on tight.
Okay, do not put your face over it.
Yeah, put your hand down there, Vince, and put your hand over it.
Tip it sideways.
And get the caps on, you can't get them
Didn't want to
off.
let go at all. There it is.
Okay, everybody who can retrieve your canisters and your caps and take them back. Thank you, Vince.
You're welcome.
It turns out,
Oh, highway, oh.
Highway.
I was gonna say, this is something that is just an example of propulsion. The fact of matter, to escape from the Earth's gravity, our rocket's gonna have to travel 25,000 miles per hour in order to escape. It's the escape velocity. And I think maybe this might be a good time to interject. How long is this whole mission to Mars going to take?
that's what I'm about to get into.
Okay, from what I've read, it's 5 months, 5 months to get to Mars. They're going to spend 50 days on Mars and spend another 50 months coming back to Earth.
Actually, it's a little bit different.
Okay, what is it?
Actually, NASA talks in terms, and we don't want to go into this with the kids,
Right.
Yeah.
NASA talks in terms of something called a Hohmann transfer, Hohmann.
I was trying to dumb it down.
A Hohmann transfer is a minimal energy situation across the board. You want to use the minimal energy that you have to get to Mars and back. And with Hohmann transfers, to begin with, it's going to take 9 months to get to Mars, so that you're on a trajectory that gets you there in 9 months. You have to stay there for 500 days until the next window opens, and then it's going to take you 9 months to get back to Earth once you're on Mars and stay there for 500 days.
The reason for that is that one Earth day is, what, 7.5 moon?
Honestly, I don't remember.
Mars days, but they're not the same. That's why it's having the two, having Mars and the closest place to Earth, which is still another 5 months away, at the closest approach. You've got one thing whipping around this large area, and another one at Earth has got a wimpy one about that much of a radius. Okay? FYI.
Thank you, Vince. Okay, the next thing that we're going to do in our bag of tricks is talking about how one generates power on Mars. Obviously, there are no generating plants on Mars. There is nothing on Mars. Even if there were a generating plant on Mars, there's no oxygen to burn the coal with. There's no nukes. Solar panels, I suppose, but remember, Mars is farther away from the sun than Earth is. So, what NASA has been doing on its mission is using fuel cells. And we're going to create a fuel cell for experiment number 3. NASA will be using oxygen and hydrogen, which somehow they have to get up there to Mars, or with chemistry to the rescue, maybe they can generate somehow oxygen and hydrogen on Mars. Remains to be seen. But in the middle of the table, there's a cup of water with some wires and pencils taped together and a battery. Okay?
Bob, I think at this point,
Yes, sir.
it's also a good time to say, we're going to get our own water from hydrogen and oxygen from our electrolytic cells, but also, they have found water on Mars, some small amount.
Yes. Yes.
Ice.
Okay, it might be a good idea to kind of put it in the middle of the table so that all the students can see it. And first thing we're going to do, it's all of this business here with the battery and the wires, salt, cup of water, and everything. First, student number 1 at each table, if you would please take the cup marked S3. It has salt in it.
S3 or S2?
I beg your pardon, it's experiment number 2. So it's S2. And pour the salt into the water, and there's a wooden stirrer there. Please stir it up to dissolve the salt. Once that is done, student number 2, maybe pass the cup down. Student number 2, put the pencils in the salt solution. Ta-da, that's it for student number 2. We got to pass the fun around to all the kids, right? Student number 3, let's take the 2 wires now. Student number 3, connect one of the wires to the lead of one of the pencils. At this point, Bob, can I borrow one of your wires?
Sure.
At this point, demonstrators, I think it would be a really good idea to point out to the 2nd to 6th graders how these wires work. These insulators are a little slippery, and the wires in there, of course, are alligator clips. The kids have got to make sure they locate where you push to open the alligator clips. Maybe practice that a couple of times, okay? And show them, demonstrate to them how it is that they open up the alligator clips. So, student number 3 put one alligator clip on one wire. Student number 4 put the other alligator clip on the other wire, and make sure they're not touching. Doesn't matter which end at this point. And student number 5, connect the 2 wires very carefully to the 2 terminals on the battery that are there. That's there. Okay. If everything is working okay, right, we should be generating chlorine at the anode and hydrogen at the cathode. So ask the students to take a second and observe the fact that bubbles are forming. There's nothing magic about this. This is just chemistry. Troubles, Vince?
You smell the chlorine too.
You can?
Yes.
Well, what we're trying to do,
Swimming pool.
yeah, what we're trying to do, gang, is to come up with some kind of a fuel cell that isn't dangerous for the kids, okay? And we're using the chlorine in the salt solution to generate chlorine gas, or the chlorine ions, to generate chlorine gas. And the chlorine and the hydrogen, as they evolve, are dissolving slightly in that brine solution. Let's let that gurgle away for about 3 minutes, and the kids can look at that and ooh and ah, Myra. Can you see that from where you are? Okay.
I would suggest that you keep your battery in a horizontal position so it doesn't become top heavy with the wire.
Okay.
And maybe fill it up quite a bit with the water so that it does stay heavy enough that it doesn't tip.
There you go.
Yeah. Good suggestion.
Or have somebody else hold it.
Yeah, have somebody hold the thing so that that cup marked W2 doesn't fall over. Now, very, very, very important. Very important. We have different colored wires here. Everybody is going to have different colors. They could be green and yellow, or white, and red, black. So what you need to tell the kids right now is to locate the negative terminal on the battery. Which one is the negative terminal?
Green.
Okay, well, it's going to be different for everybody.
Ours is green.
Locate the negative terminal,
One side.
and
There's positives and negatives on the battery on the side.
yeah, it's marked on the side of the battery. Locate the one that's negative. Remember which color wire is connected to the negative terminal. We're going to call that wire number 1. Doesn't matter what color it is, but the one connected to the negative terminal is wire number 1. Now, while that's gurgling away, let's see, have student number 5 take the red LED. There's a tiny LED on each table. Student number 5, take the LED, and before you do anything, at the base of the LED, it's kind of shaped, the head of the thing is shaped like a bell. On the rim of the bell, at one side is it's flat. Locate the flat side on the LED. You may have to look at it end on, but you'll find which side is the flat side on the LED.
I think the flat side is also associated with the shorter wire.
I think you're right. Okay? Vince, can you confirm that?
Yes.
The flat side is associated with the shorter wire. Okay, student number 5, very gently spread those 2 wires apart on the LED, maybe a 1/4 of an inch max. We're doing that so that we don't break them off in the first place. And secondly, we're going to be reconnecting the wires in just a second to that LED. At this point, we will have had the chlorine and the hydrogen forming, that electrochemical reaction is being forced by the battery. The chlorine and the hydrogen are still evolving and dissolving slightly in that brine solution. So I think at this point, which student will we have do that? Student number 5. Very carefully disconnect the wires from the battery, remembering which one was wire number 1, connected to the negative terminal, which color it was. Okay, disconnect the wires from the battery.
But, something that might be obvious to us, but not to the kids. Let's trace the path of the electricity or the energy from the battery, starting at the battery, going to are lead number 1 or 2 down into the water, through the water, back up the second pencil, and back to the battery, thereby completing what we call a circuit.
Very good, Vince, good point.
Okay.
And our electrolyte, in this case, is salt.
Okay, so now we want to put the red, or the,
Now, we're gonna disconnect the wires.
Let's disconnect them one at a time.
Yes, one at a time, very good.
So let's.
Disconnect number 1 first.
Right.
And hook it to the wire nearest the flat side of the LED, which is the shortest wire, Bob says. And now disconnect wire number 2 from the battery. Must be an alarm. Disconnect number 2 from the battery and connect it to the other side of the LED. What's happening? Don't tell me I've got them backwards after all of this.
Let's try it the other way.
Reverse the silly wires. Honestly, I thought I had them.
wait a minute.
All right.
Ours working fine.
Did you hook it up to the way I told you to in the first place?
Yes, sir.
Wire number 1 to the short one?
Mhm.
Okay, good. Yeah, maybe you've got a bad LED. There's another LED behind. Good. Yeah, check the next LED.
You know, it's used it all together.
There are not extras in the kit. It shouldn't be bubbling anymore.
Yeah,
No.
what we're doing is we're storing the energy when it's bubbling, we're storing it in the solution, and now we're drawing it all out of the solution and putting it
You won't pour out these.
What we have done, demonstrators, is we have used the battery to create a source of chlorine and hydrogen, which have dissolved in the electrochemical cell in the brine solution.
Any light?
And once the chlorine and the hydrogen have dissolved in the solution, Vince, I think she wants you to raise it up so that you can see it on the. Is it still lighting?
It's not lit because we drained the battery.
Yeah.
Yeah.
All right, let's see, that one you do it. Yeah,
So we can do it in this one, just by-
To do it again, we probably have to generate more hydrogen and more chlorine. Okay? So what we've done is once the hydrogen and the chlorine have been evolved and have dissolved sufficiently in the water, in the aqueous brine solution,
Try the other.
they're having all kinds of trouble over here.
She got LEDs.
That's not a good thing. Let me get you another one. The chlorine and the hydrogen now become the fuels for the fuel cell. NASA uses oxygen and hydrogen. Typically, we're using chlorine and hydrogen.
We got one.
Got one to work?
Well, it didn't permit it.
For a second it did. Very light.
How long did your light last?
Battery too.
Oh, I mean, we're getting fuel.
You getting anything?
Into the solution.
Except if we're heating this thing up. That's why I wonder.
You did get oxygen, chlorine and hydrogen evolving, didn't you?
Oh, yes. We had
Yes,
both.
story.
But we're actually testing it now directly from the.
Oh, they're checking theirs from the battery. Boy, I hope we don't have a lot of dead LEDs.
What number?
I think this is hard.
Remember, negative terminal to the short
Give us a
wire.
wow factor. I got the wow factor of 7.
It had a good wow factor, guys, originally, if it were.
Better.
7. Bubbles are cool.
Bubbles are cool.
And LEDs.
The LED lighting is cool if it lights.
Yeah, content.
Bob?
Yes, ma'am.
Pencils be a little different types so the electrodes
You
talk
may have,
to each other?
You may have
You may have a point there.
You may have a problem, Bob, with some of these LEDs.
Rats.
500 of them.
Oh,
but it's cool that they got it, and you can always have everybody go to that one.
Yeah.
If-
right, if out of the 5, one goes.
They've actually checked the LEDs using the battery,
Have to be in the water, right?
and they're not getting anything from here. I am sorry about that, gang. I hope we don't have a bunch of dead LEDs on our hands.
Hot.
Yeah.
What's hot?
The LED gets hot.
We're not getting-
But it doesn't
We're
light.
not getting,
Well, I guess, look,
Here, try ours.
we can at least say we're getting energy to the LED if it's getting hot, right?
Short side, right?
yeah. Oh, this is,
So,
yeah, they've got a nice one.
Is it lighting?
Yeah, it's
We need
lighting.
to pass that around.
Well, can you hold it up?
We're blowing it. Maybe Bob just generates an anti-electric field.
It's just an aura, that's what it is.
Or maybe it's not designed for when I'm testing with it.
With an iron.
Correct, with an iron.
We may be generating too much when we're blowing it.
You might, and you're blowing them up, yeah, that's a possibility.
Oh.
Anyway, let's hope that in your demonstration, Madam or Mr. Demonstrator, the LEDs do in fact light.
Yeah.
Okay, that's what they're supposed to do. If not, tell the kids that the energy is there because they're getting warm. Okay? All right. Hopefully it'll work. Let's move on to the next experiment, which is experiment number 3, a Martian spacesuit.
Now, wait a minute, let's go back up and,
Wait a minute, Vince wants to stop for a minute.
we gotta get rid of our stuff
What stuff?
from the last experiment, the saltwater.
Best laid plans in place
Right.
again.
You can just let it sit there.
So we're gonna, well, make sure it's disconnected, and if you
Yeah.
wanted, you can put that in your waste basket.
Okay, disconnect everything and we're all set to go again. All righty.
See if I can do an idea.
It's worked in the past, but who knows, maybe we had a different source of
Well,
LEDs.
I'm saying that we probably blew the LEDs with the testing. and
Could be. But you did get bubbles generating with the
We
battery.
did get
Lots of
Okay.
That was good.
Okay, Shamila, let's get back on track here, gang. I'm sorry, Lois? You can speak, Lois.
I was trying to get this to the camera.
Oh, Vince, look at the camera. Hello. Okay. Let's go to number 4, folks, okay? Can we do that? Everybody okay with that? Okay, experiment number 4 is a Martian space suit. And Carol, you're our NASA rep, so check me out on all the NASA-related stuff here, okay? And everybody is familiar with the fact that NASA uses spacesuits on the International Space Station. But if you think about the conditions that astronauts are exposed to when they're out in the vacuum of space on the International Space System, ISS, where are they? There is minimal gravity there. There's some, there's not a lot. The spacesuits that they're in are not really designed for maximum flexibility and maneuverability. Remember, the astronauts are out on a mission, an EVA as they call it, extravehicular activity, for relatively short periods of time. They're not going and living outside of the International Space Station. Shamila, where you got that focused on? Oh, okay, all right. And under the circumstances, the temperatures that our astronauts might encounter as they're doing an EVA, a spacewalk if you would, can be anywhere from plus to minus 250 degrees Fahrenheit, depending upon whether or not they're in sunlight or not. So rather extreme conditions out there. What's it going to be like on Mars, and what would be the requirements for a Martian spacesuit? Well, Vince?
Because it's further away from the sun, it's colder.
But it could be
Minus
colder.
80.
It could be colder. But one of the major features for a Martian spacesuit has got to be flexibility. Whereas the astronauts from the space station are like this, like snowmen almost, walking around out there, if you're living and working on Mars, let's say you have to go out to build a structure. You are going to be out there for quite a while, probably, or potentially. You need to be able to get around and move easily. You need to be protected from those dust storms that we talked about, which could even have micrometeorites in it. You need to be protected from the temperature, which can average 80, minus 80 Fahrenheit. So those are all of, or some of at least, of the considerations. Bob's still fooling around with the battery. Those are some of the considerations when we talk about how we would recommend that NASA design a spacesuit for Mars. What we're going to do is we're going to consider several of the fabrics that NASA actually uses in the International Spacesuit, in ISS spacesuit. We're going to consider some of those fabrics as we go through experiment number 4 here. First thing we'd like to do is recognize that there are temperature extremes that we might see, hot or potentially cold as well, and we're looking for some materials that would keep our body heat in. We're looking for materials that will be comfortable against our skin, and we're also looking for, in the end, materials that are going to resist the abrasion that we're going to see from the Martian environment. So the first thing we're going to do is everybody has 5 pieces of material in front of them. On top of that is a little cup marked P and a pencil. Bob, I'm going to give you these because I think you were missing one of the materials. Okay? There's a material that's black with a white front. That's neoprene-coated nylon. There's a purple stretchy material that is rayon spandex. There's an orange-colored material that is just canvas. There's a material that looks like a sheet of plastic film, which is Mylar. And the last of the 5 materials is a shiny version of the Mylar called Aluminized Mylar. First thing we're going to do is we're going to see, remember this spacesuit is probably going to be in layers. First thing we want to do is find which of those 5 materials feels best against your skin. So if you will take, each student, take those 5 materials and rub them against the back of your wrist. That's probably the most sensitive area of your body, the back of your wrist, in here guys, okay? That's probably a pretty sensitive area of your body. Which one would you prefer to have against your skin?
Purple one.
Purple.
Well,
What's the consensus?
Vote with your hands.
The purple one. Purple one. Okay, that is spandex. And in fact, that is exactly the material that NASA uses as the inner layer for the ISS spacesuit. Now, there is a twist. And obviously we can't use this twist here. We don't have the technology in this library setting. But what NASA does is NASA actually threads through that purple spandex material cooling coils or heating coils. And the spacesuit actually has mechanisms for pumping heating and cooling fluids through those coils. And remember, that's right up against your skin. So that has a pretty good effect of keeping you warm or cool depending on what you need. Okay? Next thing we're going to do is we're going to try to find that material that best forms a thermal barrier that will keep your body heat in and keep external heat out. So Bob Williams is going to take over this part of the demonstration. And Bob, if you would please, there's 5 cups here up on the table. that Bob's gonna use for this part of the demonstration.
While he's getting set up, I'm going to interject. When you open your kit, please be sure that you do not touch the end of the temperature dots, because they will change color instantly. If there's some that are changed already, kind of set those aside or put them in the, the one that you know is going to change anyway. And when you're holding them to cut them, be sure you're not touching those as well, because that will ruin your experiment. We noticed that some had changed a little bit when we were packaging them up.
Yeah, I'm sure Bob's gonna talk about that same thing.
Well, we have an additional issue too, and that is that initially these things had an easy open on one end, but because we cut them off to fit in the cup. I don't know if it will work inside the holder like this. So what I suggest doing is taking a scissors and cutting right along the rim, because otherwise it is difficult to get this thing on, all right? So now you have a cut here, yes, and again, I'm trying to hold it by the edge, this edge, the white edge, rather than by the thermodot. What we discovered that, I don't know if it will work. It may work inside the holder. I don't know if there's an air actuation or anything like that.
But there's no sense in doing it that way. When you can remove the wrapper from around the temperature dot, just don't touch the dots.
Yeah, and remove the wrapper, when you're setting up. Okay, so we have,
He needs help.
yeah, well, let
me hold it down for you, Bob.
Okay.
Demonstrators, you won't be doing this.
Well, they'll be doing it in advance.
By the way, demonstrators, one thing I forgot to mention, Lois, at the beginning, was there are 2 items that you need to take care of at home. Putting these cups together like this with the thermodots at home will save you a lot of time during the setup. And if you will take and separate these 5 materials from their packages into sets, 25 sets of 5 at home, that again will save you a lot of time. Those instructions are in the corrected script that's online. And the other thing you need to do is we have a filter we're going to use for the next experiment. You need to set this filter up at home. Now we prepared this last night. I just put the plastic bag that the experiment 4 came in over the top of this thing. You might want to put your filter into the plastic bag to keep the thing from drying out. But that's not Bob's experiment. Bob, who's saying it? Please note, I think it's on page 5 of the script, that those 2 things need to be done at home. Really. Okay, Bob, sorry for the interruption.
All right. You will have needed to supply a lamp of some sort, gooseneck lamp. And the other thing is you want the thing on for a while in advance so that it is hot. So what we're going to do now is going to start with the Tempedot and the clear film. And we're going to put it under there.
Does it matter which order, Bob?
No, I'm starting with the clearest ones, just so and this is the one where I expect the greatest effect for.
Okay.
All right. And we also want to, since I don't have a second hand any other way.
I can time it for you, Bob.
Okay.
How long do you want?
Let's try a minute.
A minute. Okay, go. I have, by the way, demonstrators, we have some extra gooseneck lamps.
Okay.
We ordered 3 of them, and they're here at John Carroll somewhere, along with 100-watt bulbs. But if you have a gooseneck lamp like this, please bring it to the demonstration. If not, get one from me. And please put a 100-watt bulb in it. Incandescent bulb. Sorry. 20 more seconds. You're supposed to be doing a tap dance, Bob, while this is going on.
The kids are gonna go nuts waiting.
I know. Well, we're gonna, go ahead, Bob. That's fine.
All right.
What we can do is, it doesn't say so in the script,
You know
but we
what?
can pass these around to the kids so they can see it.
Yeah, but this one is not. The ones I did, let's get any closer. You want that thing, and again, you want the lamp to have been heated up so that it is hot, because you're looking at radiant heat. All right.
Yeah, get it real close to that thing.
Was this one of the dots that, had the covering on it, or?
Yes,
We took the covering off
just took the covering off.
Okay,
to make it more sensitive to the,
I thought it was the black one. that
To the heat.
took covering off. I thought it was the black one that took the covering off.
All of them.
all of them.
Oh,
All
you
of
did,
them.
okay.
As they preset it out, they were just gonna.
Anything? This worked, trust me, it worked in our committee meetings.
This is a 100-watt bulb?
It is.
It's very important to have it running ahead of time.
Yes, it is.
Foremost.
And it really shouldn't take that long, Bob.
I agree.
So the kids that are sitting here, they're not gonna do anything more with their families?
Not yet.
Not yet, okay.
Is there something they could be doing while they're bored and waiting for this to
Yeah,
happen
why
for
don't we
5
take-
Well, yeah, there is something they could be doing. And let's have them go on and do that. The demonstrator is going to be tied up doing this, okay? So let's have the kids move on to the last part of this thing, where we're going to try to find which of those 5 materials is the one that would be the best for an outer layer for our spacesuit. Remember, for our outer layer, we want something that is tough. It will be abrasion resistant. We want it to not breathe, if you would. We want to keep the CO2 out. And let's see, what else do we want? We just wanted to stretch minimally. We don't want it to move all that much. Bob's got another light. Maybe the light's the problem. But he'll be checking that out while we're doing this. Okay, so let's take our 5 materials and first, one by one, try stretching them. See if any of them stretch. We do not want a stretchy material for the outer material. All 5 materials. Stretch them and see what happens. Remember which ones do not stretch. Or if they do stretch, we're going to eliminate them from consideration for the outer layer. Okay, everybody done that? Which ones stretched? The purple one stretched. That's going to be our inner layer anyway, so let's eliminate that from consideration for the outer layer. Let's go next to the scratch test. There are a couple of small pieces of sandpaper in the front of the table. Take those and pass them around and scratch the surfaces of each of the material. See which ones are the most scratch resistant. Yeah, you might want to cut those up and get 5 pieces. on the black and white material, scratch the black side. And each time after you've scratched, take a look at the sandpaper to see if the stuff is coming off in the sandpaper. Find the stuff that's the toughest and most resistant to scratching.
Nope, not a chance.
Greg's already got his two.
Two. Mylar.
Oh.
Mylar, yeah.
Yeah, the Mylars probably aren't a really good idea for scratching. Okay, now, I'd like for the students to work in pairs as best they can with the Mylar. Can I steal somebody's Mylar for a second? Here we go. Have one of the students hold the Mylar at arm's length, like this, and have another student take their pencil, or like this. Okay, have one student hold the pencil up, and have the other student come down on it.
Mylar.
Whoops.
This is Mylar.
And try that with all 5